Algebra 2 class, we made it through a first week and now we're on our second week of home learning. Make sure on your teacher pages that you click up on the top left to week of April 6th, because this is for Monday, April 6th. So this is our chapter 12 test review, and as I always do, I'm going to go over a good test review so that you have a real good idea of what's going to happen tomorrow for your test. So for problem 1 is about arithmetic sequences, which are both recursive in the form of a sub n equals a sub n minus 1, the last one, plus d, or they could be explicit, as in a plus n is equal to the first one, a plus 1, plus n minus 1d. Then for geometric, we can also have recursive and explicit. Recursive is a sub n is equal to r, the multiplying factor, times the last one, a n minus 1. And explicit is a sub n is the first one times n minus 1 r's multiplied together, or r to the n minus 1. Now for problem 2, we have various forms that we've used. For finite arithmetic, remember we did the sum of the first n is n over 2, the first plus the last term, because they added together when we turned them backwards, and they all added to the same a1 plus an. And that's on page 538 bottom. For the general summation notation, which we did in 12.4 last Thursday, S sub n is equal to the summation from k equals 1 to n of a sub k. And you can see that on page 539 in the middle. Now when we did finite geometric last Friday, we have S sub n is equal a sub 1, parentheses 1 minus the multiplying factor r to the n over 1 minus r in parentheses. And that can be seen on page 544 middle. Now the infinite geometric series in 12.5, r has to be less than 1 for it to converge, the multiplying factor, so the terms have to keep getting smaller. This S infinity now is the first term over 1 minus r. It's very simple, and that's on page 546 top. The infinite geometric series does what we call converges, because it has a multiplying factor greater than 1, and the terms keep getting bigger and bigger, and they add up to infinity. Now on problem 3, we're looking at page 533, example 4, where we have a sub n is the sum of the last two sequence terms, a sub n minus 1 plus a sub n minus 2, where a equals 1 and a2 equals 1. This is called the Fibonacci sequence. So the first two elements are 1 and 1, and then 2 is the sum of the two before it. 1 plus 1 is 2. 3 is the sum of 1 plus 2. 5 is the sum of 2 plus 3. 8 is the sum of 3 plus 5. And 13 is the sum of 5 plus 8. Each one is the sum of the two before it. So now on page 534, example 5, we had a simple sequence, 3 halves, comma 2, comma 5 halves, comma 3, and if you see that, that's just adding 1 half to each term. So we can represent that as a finite geometric sequence, a finite arithmetic sequence, and that's done best recursively. So an, the current term, is an minus 1, the last term, plus 1 half, and we have to specify where the first term equals 3 halves. Now, page 536, number 2, we have the sequence 3, 1, 1/3, 1/9, and there's no way we can add from term to term, so this is the multiplying factor. So we can take the second term, 1 over 3, to find the r of 1/3, and then making this a recursive geometric sequence, we can say a sub n is 1/3 times a to the n minus 1, the last term. Now on 4, we're going to ask which of the following is true for the graph of the points k, a sub k, from an arithmetic sequence which acts just like a linear function. Now we hadn't actually done much on graphs, but if we think of it as a straight line, we'll be fine. It has elements just at a equals, or the k equals 1, 2, 3, 4, 5. So is it true that all points fall on the same line? Yes, this is true, because An arithmetic sequence acts just like a straight line. Now what about the graph may be either increasing or decreasing, which is comparable to asking can it have a slope that's positive or negative, and that's true. Now how about both the domain and the range are subsets of the integers? Remember we said the domain, the element numbers are 1, 2, 3, 4, 5, 6, so the domain is integers, but the range can be anything, whole numbers, fractions, negative numbers, so they can be rational numbers, they can be fractions, so that is false, because both of them aren't. Then, is the entire graph contained in quadrant 1? Well, if it's positive slope it would, but if it's a negative slope it could be in quadrant 4. So that's false, and we're going to omit problem 5. Now on problem 6, we have to find the first, second, and 10th terms of the sequence -1 to the n times 2 to the n minus 3 over n plus 5. So we're going to work this out for each of these three terms. So a sub 1 is -1 to the 1, 2 times 1 minus 3 over 1 plus 5, and that works out as -1, 2 minus 3 or -1 over 6, which makes it positive 1/6. A sub 2 is -1 squared, which is positive 1, over 2 times 2 minus 3, 1, over 2 plus 5, 7, or 1 times 1/7 is 1/7. And a to the 10th is -1 to the 10, -1 to any even power is positive 1, over 2 times 10 minus 3, over 10 plus 5 equals 1 plus 20 minus 3, 17 over 15. So 17/15 would be the answer. Now on 7, we're asked to state the next term and write a recursive formula for the sequence, which is 1, 5, 6, 11, 17, and we're to fill in the next blank. Well, if we look at the third term, 6 is 1 plus 5, the A1 plus A2. If we look at 11 equals 5 plus 6, or the second and third terms is the fourth term. 17 is the sum of the two before it, 6 plus 11. And now we can understand that what we're doing is we're taking the current term is the last term plus the term 2 ago, which is again the Fibonacci sequence pattern, except that A1 and A2 aren't 1, but it has the same pattern. So we can say that 11 plus 17 is the next number, 28, and that solves our blank. So for problem 8, we're to state the first term and write a recursive formula for the sequence a sub n is 25n minus 13. Now a sub 1 is pretty easy to get, just substituting 1 for n equals 25 times 1 minus 13, or 25 minus 13 equals 12. And recursively, we're just saying a sub n is the last term a sub n minus 1 plus 25. The 25n is what the fixed difference is for term to term. Then 9, it asks us to write a simplified explicit formula for the sequence 15, 9, 3, -3. Now, one of the ways that we can always get the d term or the add term is to take the second minus the first, 9 minus 15 should be equal to the third minus the second, 3 minus 9, and has to be equal to the fourth minus the third, -3 minus 3, which all, of course, is -6 because it has to be consistent from term to term. So this is a -6 sequence, and now we can plug into our a sub n equals a sub 1 plus n minus 1d as the first term 15 plus n minus 1 times -6, or multiplying through 15 minus 6n plus 6, or -6n plus 21. So our a sub n is -6n plus 21. And then for problem 10, state the common ratio for the sequence. Now this is a geometric sequence because there's no way we can add anything. And sometimes the best way to do the geometric sequence is take, as we said, the second over the first, the third over the second, and that should show us the pattern. So xy the second over x squared, 1x would cancel and we get y over x. Now the third over the second, y squared over xy, 1y would cancel and we'd still have y over x. So we can see that our multiplying term, or our common ratio, is r equals y over x. Now on problem 11, we're asked to find the two geometric means between 8 and 512, which is the same as asking us to find A2 and A3 in the sequence 8, A2, A3, 512. Now this is a geometric sequence, so we can use the formula A4 equals A1 times r to the 4 minus 1. And plugging in for A4 and A1, 512 equals 8 times r to the third. And then, of course, dividing by 8, 512 divided by 8 is 64. And on my calculator, I can do 64 power 1/3 in parentheses equals 4. Because 4 times 4 times 4 equals 64. And then I can know that, looking up here, A2 is 8 times 4, because it's a times 4 sequence, is 32. A3 is 32 times 4 on the calculator, or 128. And we can see that it's really a consistent sequence because A4 equals 128 times 4, or 512. Now on 12, we want to find a sub 12 of the geometric series if a sub 3 equals 12 and a sub 6 equals -4. So let's plug into our geometric sequence formula. A sub 6 is equal to a sub 3 times r to the 6 minus 3. Or plugging in now for our numbers, we have it should be -4 over 12, -4 rather, equals 12 times r to the third, dividing both sides by 12. It should be r third equals -1/3, and r third equals -1/3. That's a mistake, but let's go with it. So now I can do a little shuffling of the numbers to say A12, which we want, is a sub 6 times r to the 12 minus 6, or using what we know r third to be, 4 times r third squared is r to the 6th, and 4 times -1/3 squared is supposed to be -1/3. -1/3 times -1/3 is 1/9. So our A12 is 4/9, and that's what we needed. So for 13, we want to find S sub 100 for the sequence 2, 4, 16, 38, the first 100 terms. Now here we know that A1 is 2, and it's easy to see that this is an add 12 sequence, so our D is 12. Now this is where we substitute into the S sub n equals n over 2 A1 plus AN, and put in AN equals A1 plus n minus 1D, and when we combine those, we get S sub n is n over 2 times 2A1 plus n minus 1D. Now plugging in the numbers we have, S100 is 100 over 2, and then in brackets 2 times 2 plus 99 times 12, and on the calculator you would do 50 parentheses 4 plus 99 times 12 close parentheses, and you should get 59,600. Now on 14, we want to find S9 for the sequence 1/3, 1, 3, 9. Well, that's easy to see that that's a times 3 sequence. So we have an A1 of a third, R equals 3, and we use the formula S sub n is A sub 1, parentheses 1 minus r to the n over 1 minus r. Now this is exactly how you do it on the calculator. 1 divide 30 in parentheses times 1 minus 3 power n in parentheses divide 1 minus 3 in parentheses, just like that. And make sure you can get 3280.33. Now on 15, we look at the sigma notation for k equals 1 to n of 3/4 times k to the k power. So 3/4 to the 1 is A1 or 3/4, and the r is 3/4 because that's what's in parentheses. And for the calculator's purposes, we can use 0.75. It's easier to enter. Now for the infinite sequence, which this is supposed to be infinite, it's a1 over 1 minus r, or 0.75 over 1 minus 0.75, which would be 3/4 over 1/4, or just 3. So that's supposed to be k equals 1 to the infinity. Now on 16, we have the summation, the finite summation of k equals 1 to 50 of the sequence term 2 minus 15k. So getting a1, 2 minus 15 times 1 is negative 13, and all we do to get a 50 is 2 minus 15 times 50, which is negative 748. So since we can get the first and the last term from the sequence, we can use our arithmetic formula. S sub 50 is 50 over 2, the first plus the last, or negative 13 plus negative 48. And all that in the calculator, 25 parentheses, negative 13 plus negative 748 should come out to negative 19,025. Now, this one is, okay, so let's see, 17. A worker completes 20 packages the first hour, 22 packages the second hour, 24th the third, and so on. How many packages does he complete during his first 8 hours? Well, we know that n is 8, the difference between numbers of packages per hour is 2, and the first term is 20. So we can use our combined formula for our arithmetic sequence. S sub n is n over 2, 2 times a1, plus n minus 1d. We use this when we don't have the a sub n. So S sub 8 is 8 over 2, 2 times the first term, 20, plus 8 minus 1, 7 times 2, or in the calculator, 4 times 40 plus 14, or 4 times 54 equals 216 for S sub 8. Now for the last one that we're going to do, problem 18, a ball is thrown straight up 100 feet in the air and rebounds 40% of its previous height on each bounce. Find the distance the ball travels both up and down before it comes to rest. Now, an S infinity, which is what we want when it comes to rest, it will be done, is a sub 1 over 1 minus r, but we want to count both up and down, so we need 2 times that sum, which will be simply 2 times 100 over 1 minus 0.4. 0.4 is equal to 40, the rebound height, and that simply comes to 200 over 0.6, or 333.333, which is really 333 1/3 foot. Now to show you how this works, A1 is 100, A2 is 100 times 0.4, which is 40, A3 is 100 times 0.4 squared, or 16, and 100 times 0.4 to the third for A4 is 6.4. And we're going to omit 19 and 20, and I'll have the test ready for you tomorrow. God bless you, keep you healthy and safe, and let's beat this coronavirus. We can do it. God bless you all. I'm praying for you.